Can you guys hear me? Good? Good over there. Hi, everyone. Thank you very much for having me out to speak. Thank you, everyone, for coming out to listen. Tonight, I will give you an overview of some of the work I did during my master's, understanding the origins of bias in word embeddings. A quick introduction. I'm a research intern here at Element AI. I'm also a graduate student over at the University of Toronto in the Vector Institute. I'm co-supervised by Ashton Anderson, who's sort of in the computational social science group, and Richard Zemmel, who is in the machine learning group. This work is sort of at the intersection of algorithmic bias, natural language processing, and explainability. And a lot of the work was done in collaboration with another student at U of T, Colleen Alcalay-Houlihan. So what's on the menu tonight? I'll start with a little bit of motivation, and then I'll give you some sort of necessary background, a quick overview of the method, then I'll dive into some of the more technical mathematical details. We'll take a break, and then we can do results and discussion. At any point along the way, please feel free to stop me and ask questions. I'll try to keep this as a discussion. I think that's what they want. It'll also make me feel less nervous if you ask questions partway through. Motivation. So there's been a lot of negative press right now around Justin Trudeau. You know, the whole SNC thing is not boding very well for the Liberal Party. And so I was going through a series of tweets related to this, and I found an interesting one that made me smile. And it's in reference to Elizabeth May, the Green Party leader. And it's saying, you know, she is actually a good leader. He is just pretty. Hashtag no planet B. And so this kind of made me smile. It also seemed like an excellent candidate for what I think of as presumptuous translation. And what do I mean by presumptuous translation? So if we take this tweet and we stick it into Google Translate, and we translate it into, say, Armenian, we get some result that I don't understand. But if I click on the Translate Back button, I should be getting the same or something close to the same result back. However, you notice here that something interesting has happened. Suddenly, our pronouns have switched. He is actually a good leader, and she is just beautiful. So what's going on? Can we find other examples of this? You know, if we take the sentences, you know, he is a nurse, she is an engineer, to and from Armenian. Suddenly, she is a nurse, and he is an engineer. You know, so why is this happening? Right, this is the question that sort of is motivating a lot of this work. You know, like I said, I don't know anything about Armenian really, other than the fact that the sort of personal pronouns are gender neutral. Okay, question? So yeah, so this is why Armenian is one of a few languages in which this will happen. But basically, Armenian is one of a few languages that does not use gendered personal pronouns. And so this roughly translates to, you know, they are a nurse, they are an engineer. And so when you click the reverse translate button, Google Translate needs to fill in the blanks and assign a gender to each of these people. And it does so sort of based on the context. And it guesses that a nurse is female, and it guesses that an engineer is male, which should raise some alarms. It's not something that we necessarily want to be programming into our algorithms. Where it comes from, at a sort of a high level, is in the actual corpus statistics that a lot of these language models end up getting trained on. So if we look at the ratio of he-she co-occurrences with all these words that I just mentioned, we see that a word like engineer is co-occurring 6.25 times more frequently with he than with she. Nurse is, you know, half as much with he as with she. Leader is a whooping 9 times more sort of likely to co-occur with he than with she. And while pretty is actually still 3 times more likely to co-occur with he, actually the base rate is that he just occurs 3.5 times more often in this corpus than she. And this corpus is actually the New York Times. It's 20 years worth of New York Times data, which is sort of somewhat shocking. And so the sort of motivating questions behind the research that I'm doing is to get a better understanding of this phenomenon and where it's coming from, and sort of a more fine-grained understanding. And there's sort of 2 reasons for this. The first is we'd like to be able to adjust models if and when these types of biases are deemed problematic, right? And when we deem them problematic is a whole other conversation, but we'd like to be able to have the tools to be able to adjust them if these biases are deemed problematic. And the other thing that's interesting is we'd like to learn more about bias generally. So this is sort of more the computational social science hat. We can think that these natural language processing algorithms are running over far more text than we could ever hope to read in 1,000 lifetimes. And so what they're learning says something about us, and we could be interested in understanding the relationships that have been absorbed. So before we get into that, I guess I need to give you a little bit of background on word embeddings and how we look at bias in word embeddings. So who here is familiar with word embeddings, just so I get a sense? OK, so that's most of you. So I'll do a quick overview. Basically, I think of word embeddings as dictionaries for machines. So in very much the same way that a dictionary has a human interpretable definition for every word in vocabulary, word embedding has a machine interpretable definition for every word in vocabulary. And the way it sort of writes these definitions is by sort of running an algorithm over a very large corpus of text. Think all of Wikipedia or all of the New York Times. And sort of embedding these words into a high-dimensional vector space and moving them around in such a way that syntactic and semantic meaning is preserved through vector arithmetic. And so if we can look at an example here, what I mean by that is like if you took the vector representation for the word king, and you subtract the vector representation for the word man, add the representation for woman, you're roughly going to end up at the point for queen in the embedding space. And so these types of relationships make word embeddings quite useful and quite interesting in natural language processing, and they're used in all kinds of downstream tasks: sentiment analysis, document classification, even sometimes in machine translation. So I guess in addition to these sort of useful relationships that get encoded, we sometimes also find these very problematic relationships. This here, man is the computer programmer as woman is the homemaker, was actually the title of a NURBS paper in 2016 that sort of first identified this and suggested some ways that we could actually explore these biases and remove them. Some follow-up work that kind of went into more rigor and started connecting these biases to psychology literature came out in Science in 2017. And what they did was they introduced a sort of a new bias metric called the word embedding association test. And I'll go into that in more detail in the next slide. But the idea is that it was inspired by the implicit association test in psychology. And that's a test that's been used sort of for many years to measure bias in humans, in human populations. And what they did is they pulled out this sort of decades of studies and found these most common biases that were being seen in groups of people, and then went into word embeddings trained on large popular corpora with this word embedding test and found that all of the same biases that were showing up in this psychology research was also showing up in word embeddings. And so these word embeddings were sort of preserving the bias that we were carrying as society. So I think I'll just dive into a little bit more detail around this word embedding association test right now. The idea is that it measures relative association between 4 different concepts. And so let's say we're interested in measuring science versus arts gender bias, right? The idea is that you create word sets that represent each one of these concepts. So you'd pick a dozen words that are related to science, a dozen words that are related to arts, a dozen words that are sort of male, and another dozen words that are female. And then you actually look at sort of a difference in differences in their similarities. Without going into the sort of the full details of the equations, I'll just give you kind of an intuitive sense for that with this diagram. So if you can imagine each of those word sets, forget about the whole set. Let's think about each set as just being a single word, okay? What we're looking at is the relative distance between these 4 words, right? So we have this embedding for science, for male, for arts, and for female. And what we want to see is the relative distance, so the difference in distances of science between male and female versus arts, male and female. So the sort of the numerator of this here is that difference of differences. I'm going to pause here because I'm getting some blank faces. Does that make sense, more or less? So what we can expect, basically, is that if science is closer to male than it is to female, and vice versa for arts, then we're going to have a positive effect size. And if the reverse is true, we're going to have a negative effect size. Yes? Is there a way to interpret the effect size? So you can associate with an effect size, you can find a p-value, essentially. And that will give you the significance of the effect size.
Could you please elaborate a little bit on the denominator that you're normalizing with?
So this is a standard deviation to account for the variability of the individual sets. Yeah, it's just a sample standard deviation. Cool? Yeah?
Because here for the f function here, you are using the cosine similarity here.
Yeah, exactly. So this is cosine similarity, and this is just sort of your standard mean.
And the WA is come from the word embedding vector itself.
Exactly.
And think about this kind of function can be directly learned from the several documents.
Can this function be learned from several documents?
Yeah, also a lot of data sets, because this is cosine similarity is just a fixed computation. This is not a data-driven method.
Well, the idea is that you're learning your word embedding first through some word embedding algorithm, and then you're.
My tuition is this kind of stuff is the fixed computation instead of the data-driven. Also, you can see that this kind of vector comes from the data sets.
Right. So your word embedding, your word representations are learned through a word embedding algorithm. Then you find these sets of words, and these sets of words are motivated by the psychology literature. It's the same sets of words that get used in the psychological testing. And then they measure the relative positions of these sets of words using cosine similarity and word embeddings, and they show that that result sort of mirrors the results that you see in psychological tests. So that brings us to sort of what I think of as the word-to-bias pipeline, which is sort of the base model that we'll be working from. On the left-hand side, you start with your training corpus, which you can, I sort of urge you to think of as a collection of documents. You run that collection of documents through some word embedding algorithm. We worked a lot with Glove. You get your word embedding, and then you, on top of that, measure bias through some bias metric. I just showed you wheat. There are other suggested bias metrics out there. And you then have some measure for bias. So that's sort of the pipeline from left to right. The research question that we've been studying is, how do individual sets of documents, individual documents or sets of documents affect the bias, right? How do they contribute to the measured bias that we see at the end of this pipeline? So a quick overview of the methodology we used. Really, this question can kind of be seen as a derivative through this pipeline, right? We're asking, what is d bias by d corpus, db by dx? And if you sort of see this, it breaks down by the chain rule into two parts. Sort of a change in the word embedding with respect to a change in the corpus, and then a change in the bias metric with respect to the word embedding, right? And as it turns out, the first part of that is quite simple, or the dB by dW is quite simple, because these bias metrics are relatively simple. They often just deal with cosine similarities. And so you can either kind of like do the math manually, use automatic differentiation, or even actually just consider, if you have access to your original embedding and a perturbed embedding, then you can just measure the difference, because running the bias metric is instantaneous. So the difficult part is that dW by dx, right? Which essentially amounts to a leave one out retraining, which would be sort of the naive way of going about doing this, right? You're trying to explore a counterfactual. You say, I have a word embedding that was trained on all these documents. I want to know what that word embedding would have been like if I had dropped some document or some subset of documents from the corpus before training, right? And of course, training word embeddings typically takes a long time. Depending on the size, it can be hours, days. And so if we wanted to really explore how the removal of each individual document one at a time would affect the bias, we could never do that in this way. And so we need to approximate that change, right? We need to approximate that counterfactual. And there's a couple options for doing that. through some tricks, potentially approach it through backprop. We instead used a method that was presented, sort of, I guess, reintroduced in a best paper in ICML 2017 called influence functions. And I'll give you a little taste about what are influence functions. What influence functions let you do is approximate how the learned optimal model parameters will change if you perturb the training data. So let me give you a little quick example in linear regression. So here, our learned models are sort of the slope and intercept of this line. Our training data is all the little points. Let's say we go in and we drag some of those points around and perturb them. We want to know how is that slope and intercept going to update. Of course, in linear regression, it's very easy. We just recompute it. In the case of word embedding, we want to approximate that. And that is what these influence functions let us do. Right? So it gives us this approximation for the change in the optimal parameters. And then when we apply that to word embeddings, we have to sort of think about things and sort of map over the problem. Word embeddings typically minimize some loss. And so your word embedding are the parameters that are minimizing some loss. The training data becomes the documents on which the embedding is learned. And then the expression, and I'll go over this in more detail later, is sort of involves a Hessian of the loss, which is very big in the case of word embeddings, and a difference of gradients. And that will give you sort of this approximation for your change in embedding. So now with these two different parts, what we can do is we can sort of score every document in a training corpus and sort of assign it a differential bias, which means sort of the document's marginal contribution to the bias. So did that make sense? Is there anything you want me to go back over for the overview there?
Maybe if you just say that last slide.
Yeah, OK. So once we have this way of approximating the change in the embedding under perturbation, and we know how the bias is going to change as a result of an embedding perturbation, we can score every document. So we can say, OK, how would the bias change if I removed document 1? How would that change if I removed document 2? How would it change if I removed document 3? And we can do that for the, millions of documents that we have in our training corpus. And then see and sort of explore, what documents are making a big difference and what documents are making, very small difference to the bias.
Big delta BI is the result of that multiplication?
Yeah.
Why is it indexed then?
So the index is maybe an overload in the notation. So this is the change in bias due to document I. Yeah. OK, so some of the technical details now. So I'll start by giving like a bit of an intuitive derivation of how influence functions come up with the result that they come up with. Okay? This is not going to be a super mathematically rigorous derivation. Influence functions predates my birth, in fact, so I'm not going to go in and try to prove it. But let's start with basically a generic machine learning problem, right? Which can be seen as you have some total loss function that is a function of your training data and some model parameters. And that is going to be the empirical mean of a bunch of point-wise losses, right? And your machine learning problem is to minimize that loss and learn the optimal parameters that minimize that loss, right? What we're trying to do then with influence functions is say, we want an approximation for theta tilde, which is the optimal parameters under some data set perturbation, training data set perturbation. And the way we can think about that, and the way they frame it in this influence function paper, is by saying we're going to add to our loss epsilon times the point-wise loss at the data point we're going to perturb. So at this perturbed version of data point k. And we're going to subtract epsilon times the loss due to that original data point. Right? And so the value we seek is this argmin with epsilon equal 1 over n, because at that point we'll have fully subtracted the original point-wise loss from that data point and added 1 over n worth of this perturbed data point. And we also note that when epsilon equals 0, this theta tilde is just amounts to our original optimal parameters. So we're sort of like fading in. We're fading out the original data point. We're fading in the perturbed data point, and the fading coefficient is epsilon, and it varies between 0 and 1 over n. That sort of makes sense? OK. So then, what we do? Oh, yeah.
Why do you want epsilon 1 over n? Why are you seeking that data point?
Right. OK. So if we look at, it's a good question. Yeah. OK. So why do we want epsilon equal 1 over n? Right. So if we look at, so if we replace this j here with our sum, right? We notice that when epsilon is 1 over n, we'll have fully removed the contribution to the total loss from zk, and added, in proportional amount the contribution from the perturbed point. OK, so more math. So now, starting with this argument expression, what they say is, let's look at the first order optimality conditions. So in order for theta tilde to minimize this, right, under certain continuity, et cetera, name all the things we need, this condition must hold, right? So we have basically that the gradient is 0. You're at an extrema, right? And what they do is they then take this expression and they Taylor expand it in theta around the point theta star, which was those existing, the learned optimal parameters we already had access to from that first baseline training of our model. And then you can go through this. We truncate this Taylor expansion at the first term, at the linear term, as we always do. And then we go through and we cross out some things that we can either ignore or that are 0. So here, this is the gradient of the loss at the learned optimal parameters, which, if we've trained to convergence, should be 0 or near 0. And then the argument that they make in the paper here is that these terms are relatively small in comparison to this full Hessian, because epsilon is varying between 0 and 1 over n. And so this is about an order of n times bigger than either of these terms. Yeah.
So relatively small plane
Yeah. ICML paper. Yeah, exactly. Yeah. So this is, at this point, I'm just sort of lifting the methodology from that paper and giving you that context that I think is just useful to understand the tools that we're applying here. And sort of through that, you're then able to get this expression for a change in sort of, the change in model parameters, right? And what it relies on basically is a Hessian term, right? The inverse Hessian of the total loss, and a difference in gradients. So if we think to word embeddings, you should be thinking that word embeddings have a lot of parameters, right? And that this Hessian is massive. And so it's a very serious computational challenge to have access to this Hessian. And so the work that we did was to figure out a way around this. The original influence function paper comes up with sort of gives a few computational methods to approximate this. None of them fit well with our particular application in word embeddings, and so we sort of took a different route around. In order to sort of understand that route, I'm going to now pull away from influence functions and give you some sort of context on glove. Again, by show of hands, how many people have played with the glove word embedding algorithm before? OK, wow, cool. All right, so GLOVE stands for Global Vectors for Word Representations. It's out of the Stanford NLP group. Basically, it learns an embedding in 3 steps. First, it extracts a vocabulary. You can sort of threshold the size of that vocabulary to V. It then constructs a co-occurrence matrix from the training data, which is you can think of as just a very large, V by V sparse matrix. And then it learns an embedding from that co-occurrence matrix. So unlike Word2Vec, it doesn't actually run the algorithm over sentences. It first constructs a co-occurrence matrix and then learns the embedding from that co-occurrence matrix. So I just want to spend a minute here on constructing that co-occurrence matrix. The idea here is that you slide a window across your corpus, right? And you're going to increment your co-occurrence matrix at the intersection of the words that co-occur. And the way they do it in Glove is they sort of weight the increment by the distance between the two words that are co-occurring. So if we look at this example, when our window is in this position, we're going to add 1 to the sort of entry for word the and word quick in our matrix. But we're only going to add 1/2 for word 42, sorry, brown and the, because they're separated. Does that make sense? Yeah? OK, great. Another thing that's worth noting, sorry. Another thing that's worth noting here is that we can actually we can find our total co-occurrence matrix by summing the co-occurrence matrix of all of our different documents. Because typically you would break, you sort of choose where to break these windows. Typically, you often use document boundaries. And so if you use document boundaries as where you're breaking these windows, then your total co-occurrence matrix is just the sum of all your individual co-occurrence matrices. All right. So if we now want to apply influence functions to Glove, we need to look at the Glove loss function. And this Glove loss function is, so the total loss is a function of your co-occurrence matrix and these 4 different model parameters. So W here is your word embedding. U is your context word embedding. In the case of a symmetric context window, those can be seen to be equivalent, actually. Not the same, but could equally be used as a word embedding. B and C are sort of bias terms in the conventional meaning of the word bias in machine learning. And so our expression looks to basically minimize the distance between the log of the co-occurrence of 2 words and the dot product of their word vectors, roughly. There's some weighting functions to deal with commonality of words. But what's important to think about here is, despite the fact that I've been talking about the corpus in terms of a sum of documents, the loss function is actually written where our data points are not documents, but the individual entries in the co-occurrence matrix. Right? So one document, even though we're maybe removing one document, that's going to result in the perturbation of multiple data points from the perspective of the Glove loss function, right? And so we need to sort of tweak that influence function equation and look at it as not just the difference between 2 gradients, but of a single perturbed point, but of a sum of perturbed points, all of the words that are going to be affected by that document that we've removed, right? And if you go back, you can work through the math is linear in this particular term, and so it works to just run through the sum. Do I still have everyone? Yes. All right, great. OK, so then the next step then is to come up with the terms that we need for the influence function approximation. And what we do is a giant leap of faith assumption, which is to treat U, B, and C as constants while we take those gradients and Hessians. And this seems kind of crazy. However, the influence function paper did show a number of results where they used influence functions on deep neural nets and treated all the early layers in the neural nets as constants and only ran it on sort of the last layers in the network and got quite good results nonetheless. And so we sort of were inspired by that and said, for the sake of these like little tiny perturbations of the corpus, we're gonna only be interested in the changes in W and act as though U, B, and C all stay constant, right? And then in that case, we can sort of then fit this loss expression into the form we need, where we create a pointwise loss and a total loss expression, right? And what's interesting to note here is that our pointwise loss now are actually the rows of the co-occurrence matrix. So they're no longer the individual entries. They're now the rows of the co-occurrence matrix, our data points. Okay? So with this pointwise loss, we go after that first term we need, which is the gradient of the pointwise loss with respect to the model parameters W. And very conveniently, what we find is a lot of sparsity, right? Because if you look at this pointwise loss, you realize that only word vector I is actually involved in the pointwise loss of co-occurrence row I. all of the gradient with respect to, or the derivative with respect to all the other parameters that are not wi are going to be 0 for that particular point-wide loss, right? And what this ends up leading to is a block diagonal Hessian. So our Hessian, which would normally be, in this case, V by V, a massive matrix, V being like maybe 100,000, maybe 3 million, becomes a bunch of little blocks that are D by D, D being the dimension of the actual word vectors. Moreover, because the bias metrics we're interested in usually only deal with a subset of the words in the vocabulary, we only actually need to figure out the updates or the changes in the model parameters or the word vectors associated with those words that we're measuring bias with, right? So, and because we have block diagonality, we have this sort of decoupling effect, and we can actually compute the change in the word vectors for each of these words independently, and that just saves us a whole lot of time. So with that, we basically, so the method then computes for every document or every perturbation, which is, let's say, the removal of a document. We first compute the change in the word vectors associated with that perturbation, just the subset of words that we need for the wheat or for whatever bias metric we're interested in. And then we just measure the change in the wheat, just apply it. We don't even need to do gradients on the bias. And that's how we come up with a score, a delta B, a differential bias for every document in the corpus. So our experimental methodology is principally around justifying this massive approximation, right? So what we want to do is make sure that this assumption we made that we could treat all these parameters as constant is reasonable, and we show that by actually exploring the ground truth counterfactual. So what that means is that we train some baseline embedding. We then approximate this differential bias for every document. We form document sets of interest, so document sets that are expected to have some sizable impact on the bias. And we sort of predict that change in bias. And then we actually remove them from the corpus, retrain the embedding, and compare our approximation with the ground truth. So there's a couple of things like mentioning multiple seeds. One thing to note is that what we found and what has been confirmed in other, I guess, work since is that word embeddings do have a lot of variance between random seeds. And so when you're looking at such small sets of cosine similarities between words, you actually need to sort of bootstrap with multiple random seeds and average over them. Otherwise, you sort of get a lot of retraining noise and a lot of variance from that retraining noise. And so we actually don't just train one embedding, we train 10 baseline embeddings, and for every ground truth, we retrain 5 times to make sure that these changes in biases are not just due to retraining noise, they're actually, there's signal in that noise. So the results and discussion will happen after a break.
Do you mind before going?
Yeah.
Do you mind repeating that, like iterating once more over the couple of things?
The full methodology?
The iteration of your experiment, yes.
Okay, so we start by training, let's say, 10 baseline embeddings, okay? And then we calculate the differential bias for every document in the corpus, right? And we use those 10 different baseline embeddings in that calculation. And so now what you've got is a score for every document. But we don't want to remove just one document at a time and retrain, because our thoughts for this experiment was we wanted to see sort of significant changes in the bias. And so we form document sets. So we look at let's say we take the 10, 100, 1,000 most influential documents, either that are going to add to the bias or remove from the bias. And we remove a chunk of them at a time. And then we repredict the differential bias for that set, because if you notice from the equations, you can't just actually, you can sum through data points, but you can't sum through documents. And so we have to repredict for that set. And then we actually get a ground truth by retraining the embedding. Again, like I said, we retrain not just once, but with 5 different random seeds. And then we compare our predictions with the ground truth.
question.
Yeah.
I just want to clarify one thing. He's showing you that his approximation, if you go to the previous slide,
Yeah.
that his approximation matches the reality of retraining. Yes, and so it's...
Oh yeah, that's
Yes.
yeah. So the whole point is that I'm trying to make sure we're going to make some approximation for how the bias should change due to the removal of a document or a set of documents, and I want to make sure that that approximation is valid by actually removing it and comparing with and retraining and comparing with that new ground truth. Yeah, exactly.
This WI comes from the document set. The WI set of words.
Yeah, okay, so we can think of the set of, here what I mean is that I'm looking at the set of word vectors that are used in your wheat bias metric. Because if you think about it, even though the entire word embedding is going to change as a result of a document removal, if your bias metric is only looking at a subset of those words, right, and is only measuring bias using a subset of those words, we don't actually care how any of the other words change. We only need to approximate how those words that are used in the bias calculation are going to change. And so that's just a sort of a further computational gain to not have to approximate how everything's going to change. We only care about a certain subset of words.
So the ultimate measure of bias comes from the field of psychology for this?
Yeah, exactly. So there's a bit of a, like if you go back to that, I won't go all the way back there, but the pipeline, right? The point here is that the bulk of the work is trying to figure out how your word, how to approximate the change in your word vectors, and then you can bolt on any bias metric you want on top of that, right? And there's been a number of them proposed. The one that I presented called the WEAT, the Word Embedding Association Test, was kind of done in collaboration with some psychologists. But there's been other metrics proposed since. And so, I think the bulk of our contributions was figuring out how to come up with this, W tilde, this perturbed word embedding in an efficient way. And then you can use, like I said, any bias metric on top of that. Further questions? Great. Thanks. All right. Okay, you got me? All right, so this is the part where I convince you that our assumption made sense and that the results are reasonable. Okay, so I'm going to look at sort of just a subset of the results that we have in the paper here, specifically the ones around what we call wheat 1, which is that science, arts, gender bias, and the ones that we've run on the New York Times corpus. So the first figure here I want to go over is the differential bias of every document in the training set. And so the idea here is this is just our approximation still at this point, right? This was that sort of second step where we compute the differential bias for every document in the corpus, and then we made a histogram of them. And what's interesting here is that this is a log scale y-axis. And so the bulk of your training documents have a very minimal impact on the bias. Actually, in fact, I've actually removed the bucket corresponding to 0, which goes up even higher. So the idea here is that what we are interested in are the tails of this histogram, which are the influential documents that seem to have a disproportionate impact on the bias, or a much higher impact than all the other documents. And it's actually from these tails that we construct the perturbation sets that we then actually explore the ground truth retraining with. All right, so this is a plot of validation. So what we've done now is we've constructed different size document sets from those tails, and we approximate the impact of their removal, and that's on the y-axis, and then we validate the impact of their removal by actually removing them and retraining the word embedding, right? And so what you see is quite a strong correlation between our approximation and the actual change in bias. And what these little sort of tails on our points are standard deviations associated with, like I said, we were doing everything with multiple random seeds. So we were training multiple baselines and multiple, so retraining multiple ground truths and making predictions for multiple baselines. And so you sort of see a sense of the standard deviations. There's another way to sort of show this data, and that's this plot here. Okay, so this is a little bit more explicit. What we start with in the middle is this is your baseline embedding, so unperturbed. We've removed 0 documents, all right? And the idea is that, I've trained it with 10 different random seeds. This diamond represents the mean, and that's your mean wheat bias right here. And then each one of these sets was one of the sets we constructed by removing documents from those tails. We named them by scenarios. Like scenario increase 100 was removing 100 documents in a way that we expected would increase the bias. Decrease 300 was removing 300 documents in a way that we expected would decrease the bias, right? And so, and when I say decrease or increase the bias, I mean either drive the effect size, more towards positive, a bigger effect size, or drive the effect size down or even negative, right? And what we sort of see here is that in blue, we have our approximations, and mirrored very closely underneath, we have, just above, is the validation, is the actual retraining. And so again, you can see for every point, there's some variance, but there's sort of a clear signal that's moving through the noise here, and our approximations sort of mirror the ground truth quite well. One thing that's worth noting is that we've actually gone from an effect size of whatever it is, 1.3, 1.2, and moved it all the way to sort of like negative 1.3, just by removing a subset of the corpus that corresponds to 0.7% of the corpus. And so that removal was so insignificant that we didn't actually see any performance decrease on the analogy test that we'd run the embeddings through. So we're not removing the word embedding sort of predictive capacity or its representational capacity with this sort of limited corpus removal, but we are completely driving the bias in the other direction. That raises a whole lot of other discussion. We're skeptical that these wheat bias metrics are robust enough for this type of analysis after having done this now, because we feel like you shouldn't be able to reverse, science and arts gender bias in the entire New York Times by just removing 0.7% of the corpus. And so we're skeptical of sort of reading into too much of the results, but from the perspective of actually hacking the metric, we've certainly been able to hack the metric and drive it completely the other way. You might be interested in knowing a little bit about what documents are in the tails. That's sort of a typical question that people have. And so we did like a qualitative analysis of the documents that pop up, those very bias influencing documents. And they do, for the most part, seem to align with, like, their semantic meaning seems to align with the way we would expect them to impact bias. So it's like, bias decreasing documents, for example, it's an article about women in astronomy. So it's connecting women in science, right? Whereas bias increasing documents, this guy, a famous male astronomer. There was some other stuff, I cut the lists off here, but, or you see like male authors, connecting men in arts, So the actual documents that come up, for the most part, there's obviously some exceptions so that we'd sort of call like co-occurrence anomalies, do sort of make intuitive sense. Another question we had and we wanted to sort of explore is find these document sets we've identified, change the bias in in glove, but what if we removed them and trained word-to-vec embeddings? Would we see a similar impact on bias? And so that's what this does. This is looking at sort of word-to-vec and the PPMI representation, which is sort of a non-embedded word vector in some way. But two different ways of representing relationships between words. And what we see is that these are the same sets of documents we identified in glove, and then we remove them from word2vec and see how the wheat changes. And what we see is that you see like a dampened change, but that mirrors the same shape of the curve. So these documents are less effective at removing or altering bias in word2vec, but still have an impressive impact. Like you take this effect size down from 1 point, whatever it started at there at word2vec, 1.3, 1.4, and bring it all the way down to almost 0. So there's something to these documents. We're capturing, there's something here. And what else do I got here for you? OK, so this is going to be a little bit more. Here we're actually looking at another bias metric. So other papers have proposed measuring bias by like constructing linear axes that represent concepts. Like in the case of gender, you could look at a gender axis. And then what you do is you can kind of like project your words down onto that single dimensional gender axis and see how the model has implicitly gendered every word in your embedding, right? And so we construct a gender axis, and then we project the target words that we used in the wheat onto that gender axis. And you see in black here is that baseline embedding, and you see these arts terms tend to fall sort of more on the female side, and the science terms tend to fall more on the male side, corresponding to that baseline effect size. And then when these are the impact of removing those maximum scenarios, the 10,000 most bias increasing or most bias decreasing documents, and seeing how those projections change. And so, sort of as expected, the science words under the removal of the bias decreasing documents become more male, and the arts ones become more female, and vice versa when we remove the bias increasing documents. Yeah.
Why was there such a significant increase in astronomy? Is it like that it's not scaled, and then removing it changed that?
So that's an excellent question, and that's sort of been. This is why we are very skeptical of sort of the wheat metric in this analysis. And what I've done here is I've put in parentheses the total counts of each of these words in the corpus. And you notice here astronomy is the rarest word in that set. And as a result, it is most hackable, right? So if it only shows up 3,000 times, when you remove 10,000 documents, you can, either you can almost completely remove astronomy, or you can leave only astronomy co-occurring with a handful of either male or female words, and thereby really drive it in one direction or another, right? And so actually what we found was that there was a strong correlation between the amount words moved, the representation of words changed, and their frequency in the corpus, right? So this method was sort of acting through rarer words. which has led a bunch of sort of future work at this point where we're exploring like weighted versions of the wheat, versions that deal with much larger word sets, and are trying to sort of prevent this type of like hacking rare words. So I think that's all I got for you. A quick recap, basically. Bias can be quantified in word embeddings and has been shown to correlate with known human biases. We can approximate how corpus perturbations affect these biases using influence functions. That's the sort of the bulk of our technical contribution. We can then identify sets of documents that are most responsible for any given bias. And then what we find is that these documents are sort of meaningful both in the sense that they affect other bias metrics and other word embedding models, but also have sort of a qualitative analysis piece to them that makes sense. So that's pretty much it for me. We have a few discussion points that have been suggested by our facilitators. And I don't know if I pass the mic over to you or just open the floor.
Yeah.
Thank you for the talk.
Yeah. So this talk has been mostly focused on, detecting bias, but I think it would be important for all of us to think about how we define bias. If we define bias as more importance or considering more weights for some attributes of the data compared to another one, we can say that all of the things that the learning algorithm is doing is detecting different types of bias. For instance, if we have a classifier for recognizing horses versus zebras, if the classifier is trained and is biased towards recognizing animals with a stripy pattern as zebra, we can define this also as a type of, as sort of bias. But what type of bias is undesirable here? It's important, we can have a discussion about what are the inappropriate biases. And also, now we have detected the bias in the algorithm, how we can remove these unwanted biases. And also, some of the biases are noun. Here we specifically targeted gender bias. But some of the biases are not noun, or maybe they are more specific to machines, not humans. How we can detect those sort of not predefined set of biases. And you have also some
Okay.
other discussion points?
Well, yeah, so based on his talk and with the question regarding astronomy, okay, we can see how bias is actually exacerbated by just a few data points, okay? You can essentially hack the metric, as Marc mentioned, by removing a very, very small number of documents in relation to the total amount of documents you have in the entire corpus, okay, and basically remove the bias, right? And so the discussion point that I'm putting forward is there are some extreme data points that you're having in your corpus that are probably driving most of the bias. It's sort of like the 20%, 80% rule, right? 80% of your bias is driven by 20% of your documents. In this case, it seems like 1% and 99%. 1% of your documents are driving 99% of your bias, okay? And so, yeah, based on that, I was thinking that maybe in society, you've got all of us people, if you have us as a collective, okay, we all have some sort of norm, we have we like if you just average everyone's, let's say, mentalities and biases, you get at some norm. But there will be a few people who've got like biases here and there, and so these people are probably the ones who shape society. Okay. Something for people to think and reflect upon, okay? Yeah, the change in society doesn't happen because of the ones that are in the norm. It probably happens because of the people who are at the extremes, okay? The second discussion point is Bias largely depends on our cultural norms, and so.
Before you go forward, can you explain your last point a little more?
Well, I was just thinking that maybe maybe it's just some food for thought. Okay, that because most of people in the society, by definition, follow a norm. Okay, if you want to do some biasing or de-biasing, both ways, you need to remove people at the extremes. Okay, or people at the extremes have to take action. You know what I mean? It's more of a food for thought kind of thing. I'm not trying to put forward anything. Okay, it's just that sometimes you say that people who drive change are actually the ones that are the number of people who are driving change are actually the few ones that are the outsiders. You know, the few outsider ones, not the majority. The majority tends to follow later on.
Can you give an example?
Okay. So for example, let's talk about the Industrial Revolution. Okay. It was So most people, for example, still lived as farmers, right? And but you had a few, for example, entrepreneurs in England. Okay, they figured out that hey, I can make this go 10 times faster and 10 times cheaper by having a machine do it for me. Okay, let's start this industrialization thing going on. And so, in the beginning, it's not accepted. Okay, the norm is still agriculture. Yet, for example, nowadays, 1% of people are working in agriculture and providing food for everyone else. Okay, and so I think industrialization is just one part of it, one example of that. We can talk about tech. Is just another example of that. Okay, so it's just some people with some sort of vision that is extreme, and we're not saying that some extreme views are bad, some extreme views are good, I guess, for the collective. And so that's, I guess, the food for thought that I'm trying to. Did it make you think? Yeah, it is making you think. So I'm doing my job well.
I wanted to add some points.
Well, yeah, he's good.
So one thing that I want that's like a big question right now in my head is distinguishing between intention and the actual bias, right? So when you have a lot of documents, when you have like a big corpus, okay, based on my own experience playing around with like fake news or hate speech, right? I've played around like how to detect or make a classifier to understand how fake news is getting published or how hate speech is being sort of propagated on Twitter, right? Right. So here also like I think I could find some similarity here that okay, association of the words doesn't necessarily mean that that doesn't necessarily represent biasness in a document. So we could go one step further and then look at the actual intention of the document. If the intention of the document says that is based like on a bias maybe idea or like approaching maybe a topic with a biased approach or with a biased sort of attitude, then we can say okay, that document is biased towards some specific topic. But sometimes there might be a document that like the association of the words maybe somehow represents the biasness, but the intention of the document is not biasness. So what do you think about this?
Right, okay. So I think capturing the difference there between sort of I guess direct or intentional bias and almost like contextual or environmental bias, I think is very interesting in the context of word embeddings or any kind of like NLP. I guess, so one of the things we tried to do was with the qualitative analysis was to see, if the semantic intention of the documents to some extent aligned with the bias we're measuring. And in some cases they did, in some cases they did less or didn't at all, right? However, and this is sort of an argument that gets made in that science paper talking about like that introduced the wheat, which is to say that like the direct or intentional bias is really only a small part of the story, and that fine, maybe in the New York Times, that 20 data of New York Times data, none of the articles said explicitly, men are leaders, women are, not leaders. But when it's 9 times more likely that the word leader shows up with male pronouns in its context. That's got to say something about society. That's another kind of bias, you know. And if you read through that and you absorb that, their argument to some extent was that we're actually more sensitive to those types of contextual biases than we are to those direct intentional biases. That we end up absorbing those contextual biases. You know, we read the New York Times for years and years and years and years, and just every time we see the word leader, it's about a male leader, and then without anyone, you know, you wouldn't agree that you think, you know, leaders are necessarily male. But because you've seen it over and over again, implicitly you've taken that bias on, and then when you're studied through a psychological test like the implicit association test, lo and behold, it pops out. They're able to see that. And so, yeah, I mean, I don't know if that fully answers your question, but I think the distinction is important. But I think both types of biases are you know, very important biases to be considering through this type of analysis.
So, just a quick follow-up. So, in case of the astronomy, right? So, when you associate like the word astronomy with like male sort of part of the whole story, so maybe this is something that like this is the fact, right? I mean.
So yeah, okay. So I mean, I think this is where there's a whole political conversation that needs to happen and a sociological conversation that needs to happen in terms of what biases are problematic and not problematic. And I mean, so when we went through this work, we studied a couple of biases. I only brought up the gender bias here, but we also looked at like a bias like weapons versus instruments, which sort of looked at weapons, instruments, pleasant words, and unpleasant words. And we found, lo and behold, you know, instruments are more associated with pleasant terms and pleasant ideas, and instruments are more associated with pleasant, and weapons are more associated with unpleasant, right? And so this concept of bias doesn't necessarily need to be problematic, doesn't need to be, but I think the point is that they exist in all the different forms all over the place, and this tool is both, like I said, to sort of study that, and then also to potentially change that and make interventions in situations where we deem them inappropriate.
Just one thing, mention race.
Yeah, sure. I skipped the slides, but yeah, there's been a bunch of other like work looking at all kinds of other forms of bias, racial bias, religious biases, age bias, all kinds of stuff. Yeah.
So I just want to add a quick point, and then we'll go to Farhan over there. Yes, things can be considered as facts, but let's remember that these facts are the artifacts of how the society has worked for a long time, right? So traditionally, like historically, maybe women were put in such and such role, so they never got the chance to actually, you know, flourish in the roles that they can also, you know, do great at, right? So, I think it's by just saying that, it could be just a fact out there. It doesn't have. It could be the status quo, but not necessarily the facts. So, like, I mean, facts are that women could also run, right? And a lot of people objected to that, like a few decades ago. I just wanted to put it out there.
And I mean, building on that, you know, choosing to train your word embedding on, you know, 20 years of New York Times data that is 40 years old, like, is choosing what facts you build your model with, right? And so, choosing what facts we're going to build our model with is like a conscious choice, and we have to just be aware that we're introducing a bias that comes from the choice of facts. And so I think, yeah, we need to be careful how we craft those things.
I know there are a lot of questions, but Farhan wanted to say something.
So my understanding is that, first of all, thank you for the approximation technique. Is quite useful.
Can you speak up, please?
Yeah. First of all, I would like to thank you for the approximation technique because it's a lot of burden. But in terms of the biases, the first one, what I understood in this presentation is the first, we have this layer of cognitive biases that I guess is not biases, that the factual truth of our understandings of our environments. Because and they're somehow projected in the way we speak, and some of them are projected through the samples that you have, for example, through New York Times or other stuff, which is another level. Then you want to capture these biases in this, and then want to subsample it from other things that you have. And we say, okay, you could capture the whole bias in the, for example, New York Times corpus that you have, and then you want to say that, okay, this is the factual biases that there's, you see my point?
I might pause you there. I just don't know if any of these biases are factual in the sense that, like, they're all associations that we've made, right? So they're only factual in the sense that they like the corpus statistics, you can't argue with them, I guess, in the sense that these are the statistics of the corpus, but there's nothing factual about those associations. Those are cognitive associations that we've made. And I guess there's a kind of a vicious cycle there where it's like we learn these associations by reading documents, and then we kind of propagate them by writing documents that sort of mirror the documents we've read, right? But yeah, so I guess I'm struggling. So you're saying, so if we're talking about these large-scale corpus statistics, and then you're sort of talking about things that come out of that, what do you mean by that?
We are now trying to find out the biases in terms of the usage of words between one another. We try to find the biases in terms of usage of words from one to another, right? So we should imagine that there's a ground truth that each word should occur with, for example, man with leader should occur, for example, 10 times in the whole words that people speak, in the ground truth that we have. Okay?
The ground truth being the corpus, you're saying?
Not the corpus, the ground truth that we have, but the corpus is a sample for that truth.
I just don't know if there is a ground truth beyond that, right? Like I just don't know if there's
exactly,
a ground
because,
truth beyond.
For example, you have this New York Times, and then all of your understanding of bias is through the project, through the
New York Times author's perspective. Yeah, exactly. So this tool is looking through the lens of the corpus, and that's where I think it becomes really interesting, because I could never read 20 years of New York Times data, and I could never do any kind of reasonable analysis on 20 years of New York Times data without summarizing it with some kind of tool like this.
I understand your point,
yeah.
But the thing is that, okay, because of the corpus that you have chosen, you have already some biases, right?
Sure.
So if you want to say that, okay, I will try to compare it to something without any bias, so you have to, for example, have the population of all the corpuses. So it's not possible, so you are already doing a sampling. So by that sampling, then you will have a systematic bias in your system.
I think in theory there's a nice idea there where you're saying like you're going to sample your data set from some underlying distribution, and we want access to that underlying distribution, and somehow that's a ground truth. But I just don't know if it's that clean. I don't know if it's that clean in the context of.
If you go through the entire web, you're still going to be biased.
I mean,
because people are biased.
You had a super interesting result in the paper that sometimes you might think that biases are the reflection of human biases in the data, the biases captured by the algorithm. But the example that you had for weapon and instrument, the bias score that they've detected for Wiki data set for weapon and instrument is much less than the gender bias score that we see in
Wikipedia. Yeah. In simple English Wikipedia, which is a subset of Wikipedia. But yeah.
So just to do a quick recap, so the question was, maybe it's a sampling bias that you're facing?
I say that we have no matter what we do, we already have some biases. So in here you are trying to somehow compare these biases which are uncertain themselves because they are compared to the ground truth. Maybe they are, for example, correct. For example, maybe New York Times is quite proportional. The proportion of male and leadership is high. So you have already this bias, then you try to find out, okay, what article in this New York Times in 20 years have contributed more to that bias, but you cannot find out the ground truth bias.
Right. I think there was a question here too. Yeah.
So I was just at the beginning that you show the motivation by showing that tweet, right? The translation.
Yeah.
Yeah. So I was just thinking when they mentioned the bias thing, like even with the method that in your paper or other similar methods, like the problem in the beginning is still unsolved.
So that particular machine translation problem you're saying is unsolved?
Right, because when you think about that it's gender neutral pronoun in the other language, right? When you translate it back, regardless whether you have the bias removal now, like you don't know which one is the correct answer. It can be he or she or she or he, right?
Right.
I was just motivated.
So it's obviously you're sort of damned if you do, damned if you don't in that situation, right? You're forcing into sort of a gender binary, and there's a whole other conversation, I guess, around that. But what Google Translate has done now for certain languages that have gender neutral pronouns, I don't think Armenian yet, but they've actually introduced gender-specific translations. And so rather than giving you a single translation, they'll say, oh, here we've assigned this person this gender, and here's another translation where we assign them a different gender. And so they kind of give you two alternatives to precisely kind of try to combat this situation where instead of assuming gender on a very short context and making these kind of problematic associations, they give you,
But I think the argument was that it's more probable for this nurse to be translated as a she, for example, right? That was the basis of the argument.
Right.
And then now if you remove bias, then it should be then equally probable for the nurse to be translated.
Right, so even if you do have equally probable, you're still stuck in a situation where it's like,
because you don't know which one.
So you still need to come up with some, is it maybe you sample from, sometimes, I think you probably want deterministic translations, and so their way of addressing the problem was to go with this kind of gender neutral approach. Yeah.
Okay, you had a few questions over here. Russell, do you want to go first?
Yeah, sure. I'm just curious, because you said, what was it, like 40 years of New York Times or 20 years?
20 years of New York Times.
Did you look at if gender and year was correlated, like if it was reduced bias over time?
Right. So that's some of the work we're hoping to do now. The sort of initial work does not seem to show a significant difference across the 20 years of data. But I guess we were interested in getting larger spans than that, the 40 years of data. Also, I think it'd be interesting to make comparisons across news media sources, to be honest. Let's compare the New York Times with some other newspaper and see how all of these biases show up. And, so.
So this would be a great, really cool technique for making algorithms less biased. But I'd be worried that I think Nasser mentioned that you might identify your most biased documents and they aren't biased at all. They just happen to have a higher frequency of those terms. So
there's a bunch of concerns, and I think that one of the big things is trying to debias a word embedding before a downstream task doesn't really make a lot of sense to begin with, because when you're using the word embedding for the sake of the word embedding, you're interested in understanding something about your corpus, right? And it's only when you plug that word embedding as sort of a feature representation into some downstream task that you then are concerned with how bias is going to show up, like in translation or CV scanning or sentiment analysis. There's been examples of sentiment analysis where you switch the actor names from male to female and the reviews go down or something things like that. So I think the debiasing really needs to be done in the context of the downstream task.
Still, if you depict word embeddings in vector space, you could still notice these biases, right? If you bring the dimensionality down.
Yeah, for sure. Yeah.
There's a question.
One thing you might take into account is that corpus writing style. New York Times has been known to be more narrative storytelling.
Yeah.
So compared to Toronto Star, Toronto Sun, they give more discretion to author, writer. So if the corpus is mainly editorial, then there will be more subjective kind of side from the writer.
Right.
So I think you might.
So you'd be expecting to see more bias essentially, might be, as opposed to more objective writing style.
The writing style might be something that you want to consider.
What's interesting is that if you run this on Wikipedia, which is supposed to be a very objective writing style, you'll still see a lot of these biases pop out very strongly. This gender, science arts gender bias is very strong in Wikipedia. Yeah.
If there is just...
Sorry, there was a question? There was an... It was first.
So I had a question about weak score. I was wondering if the performance could be different, different kinds of biases.
So you're saying there's a methodology performance differ?
Not the methodology, but methodology should be the same, right?
The methodology is the same. In our paper, we include results for 2 different biases on 2 different corpuses. So, and we see very similar things in each of those sort of 4 different cases. But sorry, I don't quite know what you mean by this.
So, for example, if you're not focusing on gender bias, right? If we're focusing on, I don't know, bandwagon, kind of bias, would the performance be different? Would the score be, the confidence in the score would be lower?
The confidence in the score. So, you expect for different biases to see different effect sizes. That's sort of, that's what you hope. If your metrics in any way calibrated, you want your effect sizes to vary depending on the amount of bias in the corpus. And then the confidence that you have in that bias can be computed by an associated value that I don't talk about in this, which is the p-value of that effect size, which they compute by like randomly switching the words in the set with other random words, essentially. And so what's the probability of just getting that effect size from pulling random words from your document?
So this could facilitate later questions. Do you want to do a quick recap or just name what was your ground truth? What is the association, the wheat association metric that you compared the biases against, or?
Sorry, what do you mean by that?
So what was your ground truth?
So the ground truth in like throughout most of this was just one of two corpora. So some subset of Wikipedia or the New York Times. And we just train word embeddings on those corpora, and then we measure biases and on those unperturbed corpuses. And we look at the list of biases that were sort of put forward by that science paper in 2017 that measured, there were sort of a bunch of sets from psychology. And there's a list of about a dozen different, word embedding association test sets.
So when you say measured biases, is that the association of some words with regard to each other? And
exactly.
That's
So when we're measuring the bias, we're looking at these, these 4 different concepts that come up into a set, right? And then we want to see the difference in the association between those different concepts, and that is what we call bias.
Yeah, and probably, Mike, you have good points to yeah.
It's a relative deviation. I think it's the key point.
Yeah, it's a relative deviation. Yeah,
there is no ground truth.
Right,
ground truth
exactly.
is just
it's always
wherever your arbitrary marker is,
yeah.
that happens to be the baseline.
Yeah.
Great. Yeah. Well, I think what I wanted to emphasize is that in psychology and also in NLP, we use these association metrics all over the place, and the reason for that is they're very reliable. So I've participated as a subject in an experiment where they proved to me that I had some racial biases after the experiment. Sadly, I mean, probably I shouldn't have gone on the record. But it was very interesting, and it's just very interesting to note how much damage frequency can do to you, right? And just saying those, just me saying this group of people aren't this. If I say it quite enough time, this is kind of, even though I'm saying are not, this may still have the effect on you because you're associating this group with that concept, and it's very sort of low level in your thinking process. Just wanted to put it out there. Did we have other questions?
I think you could try like another technique to remove bias. Would it be effective maybe to try, say you had some ability to reverse gender in a whole document? Could you take these high-risk documents and try reversing gender in them, and then maybe duplicating it or doing something?
And then like putting them back in with a reverse gender. Interesting. Okay, so he's suggesting other ways that we could potentially, reverse or remove bias in these embeddings by looking at these high influence documents and not just removing them, but instead like swapping the gender role, of all the individuals named in those articles. And I haven't tried that in particular. We've done some interesting things though, where we've like gone to your corpus and removed all gendered pronouns. So just getting rid of like he and she, replacing it with like they, like all your gendered pronouns, and seeing how that actually impacts a variety of different gender biases. It doesn't have a serious effect on it, it seems, actually, which was very surprising to us. What ends up happening is that these associations end up getting formed through like names and through gendered words, like waiter, waitress, or whatever, and so it actually becomes very difficult. You have to go in and remove all first names, all like to really get rid of these gender associations. So, yeah.
And something related to removing this gender specific is that it's been known that if you have a set of protected attributes in your data, for instance, you want to approve mortgage, and you have one of your features is race, and you don't want your model to pay attention to race, and you want your model to ignore it. If you remove race from your features and train your model can basically recover the information about race from the rest of your features. And the best practice usually is to keep race as the feature set and train your model so that your model doesn't learn to retrieve this feature from the rest of the data. And then during the inference time, we don't feed any information or something, race neutral information as the input feature.
Right. Yeah, there's a whole world of work around like fair classification, and yeah, and this I guess touches on it to some extent. But
when you were going back to testing the validation of the metric that you used to assess bias, like way at the beginning, and testing it to some like standardized psychology tests, were there any topics that you found didn't match using the?
Okay, so that wasn't our work. That was the work that was published in that Science article, and they, I mean, I don't know if it's whatever positive result publication bias. I mean, they seem to find that all of their tests matched, and I mean, they went so far as to say that perhaps all of human cognitive biases are actually encapsulated in the corpora we produce, and that by we can just look at the work that we've written over the last 50 years, and we should be able to see all of these biases by measuring it, which is, I mean, it's an interesting and very lofty kind of result, but yeah.
On the flip side of that, and I think to kind of push on both of your points, when I actually, it's funny because I also come from a cognitive background as well, and I guess that's implicit because they don't know that you come from a cognitive background. But I actually think of everything just as bias. So the question of what do we actually mean by bias? Cognition actually just is bias, full flat.
Right.
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 So the loading here, there's so much weird loading going on here in terms of the term. I don't know. I would call it structured organization. Right, and then you can have a political valence or not.
Right. I think that's a good point. I mean, word embeddings essentially are just, they're an implicit definition, right? It's like word embeddings only have meaning because it's the position of all these words relative to each other. So it's like everything that's been learned is in terms of relative bias, right? And so, yeah, I mean, I think it's or structured organization, or whatever you said that. I like that. And so, yeah, it's true that not all of this is a problem, and we just need to have another conversation, probably without just machine learning and data science people in the room, around which biases are okay to keep in these models and which ones we should be driving out.
So there was a question over there that I sort of.
It's okay. I guess it's kind of been touched on, but I was thinking if the fact is that there are more male leaders, right, then it wasn't actually biased. It is society is biased, but the document itself isn't. So it seems like you're manipulating something externally, and in a way you're actually the one that's biased.
Interesting.
Kind of touched. Good Socratic argument. So I think that this was raised. That's what you said was touched upon before. So I think there is no inherent reason. For example, if you put a woman here, put a man there, there is no inherent reason why we should think that this person can run and we can have a contest for this person to run a marathon and not for the other, right? So factually. And these biases, that is true. They are an artifact of years of people living and thinking in such a way. So by just saying that the status quo is this, so I just want to draw a distinction between status quo and fact, right? Sorry, that was my comment.
Yeah, or maybe just a quick follow-up on that. I think the idea of a leader, I mean, leadership takes place in all kinds of different ways in all kinds of different positions. And I think it does say something about if we're only writing about the leadership roles in which men are filling, then that might also say something about author bias as opposed to just the manipulation of trying to reverse that.
Sorry, Jane.
Oh yeah, just kind of summarizing what has happened here and the question of the translation from English to Armenian and Armenian to English. It's like the fact versus bias dichotomy exists if, let's say, the translation gave you 90% of the time would translate to male leader and then 10% of the time to female leader, but then it's making that biased decision to say 100% of the time we're going to translate male to leader. in like that context.
Oh, interesting. Right.
The statistical way / the factual way would be that probability approach that exists in our texts and our data and our society, but like that not being the case makes it a bias more so than a fact.
Touché.
Yeah.
I just want to have the comment for the research. Probably you make the divide the data set with the different timelines, so you probably can observe the bias evolution with this time.
So you're asking about, yeah, so I think this question came up earlier. So basically you're saying if we divided our corpus into, let's say, decades or half decades and trained individual embeddings on each of those and wanted to measure the change in bias through time. So we've done a little bit of work on that in these particular corpora and haven't seen a strong, at least under the bias metrics that we were looking at or the biases that we were looking for, we didn't see a strong change in time. It's not a lot of time. There has been some work, I think Will Hamilton did a bunch of work on the change of a meaning in words through time in this way. And so I'm sure you could kind of apply it in a similar situation here. Yeah.
Okay, there are a couple of YouTube questions. Let's start from here. All right. What if we change the way we represent the pair that defines our vector?
Oh, interesting. The way that we the pair that represents our vector.
So they have an example. They put women and man in a square bracket, and then an arrow towards leader, and then anybody towards leader. I think that's what they're saying. It's replacing.
So I guess that's very similar to what you covered before, that you talked about how you might remove some of the pronouns to be like replace he's with she's, etc.
Yeah.
etc. I guess that's essentially what you're saying there.
I see.
Right, and I mean maybe also to answer this more broadly, evidently you're trying to represent a concept like male or like science with a subset of words, right? And so all of your analysis is going to be dependent on your choice of subset of words that you've picked to represent that concept, right? So is there sensitivity to that? There definitely is, yeah, for sure. And so, and that's where we're trying to do some work around using larger subsets and weighting them by word frequency, so we can't just hack the metric with rare words and sort of expanding on that.
And it was also raised earlier that you can't really go through the entire corpus and find anything that makes that association, at least manually or on a rule-based basis, right? So it was raised earlier that what if you go and replace, I don't know, man or woman, or he or she with they,
right,
for example, right?
Yeah.
But it gets tedious quite fast, right? It seems like it's a rule-based approach towards.
Well, or it's just ineffective, I think. I mean, you can very quickly replace you find and replace your words to your corpus. But I think the point is that it ends up getting encoded through different words,
Yes. And predicting everything then is a little bit tedious, right?
Right.
So if it's I'm just like thinking, if this is a gender neutral language, then this will not be a problem.
So I think we're saying the opposite.
Yeah, it still happens because names. Yeah. Yeah.
Not just the problem.
Names would be a way that gender bias. And again, so all of this conversation has been around gender bias. I think it's important to just like a bunch of other biases exist here as well, right? I just focused on gender bias, a particular kind of gender bias. But so even in a gender neutral language, even if you could solve this problem with just removing pronouns, you'd still have all kinds of other things that would exist. Yeah. So.
So just to draw a quick point, then I go to you. So linguists have this way of saying that grammatical gender is really different from the gender out in the outer world. So I think that could be relevant to it.
Yeah, I guess my question is a bit similar. Like if you run this on, say, Spanish language, would you expect the same kind of result? Because there you have like the words have more female, male into it, like built into it.
That's a great question, and I guess I speak French, and so in French as well. And I actually haven't tried running this on a French corpus because I imagine you would skew a lot of your ability to measure gender bias by introducing all of these gendered like sort of arbitrary words, like la table, the female table. You know what I mean? It's just like with all of every single sort of object being gendered, what would that do? Would that create sort of too much noise to be able to capture these things? I don't know. Yeah.
So you're saying it would even be too difficult to even measure it because
I don't know. I haven't tried it yet. Yeah. But it's definitely a good point. Yeah.
Have you looked at all at baseline vectors? Because you have, you can basically find vectors that are close to everything, often.
Oh, interesting.
There's a mathematics crew based out of the government that's been doing some interesting stuff, and they found that, you know how you're basically able to say that, I don't know, men occurred 3 times more often than women in the New York Times? You can actually do similar kinds of things with vectors where you basically find, well, this is a vector that's approximate to all of these structures and sort of binds them in a weird way, or an embedding, not a vector.
Oh, interesting.
Yeah,
Okay.
Yeah. So there are weird sort of statistical properties that you can actually exploit, especially depending on what the actual shape of the underlying structure is. So cosine, you're usually looking at a ball, for example.
Yeah.
You don't have to have a ball. You could have a cube.
Right. Okay. Okay.
So
Yeah.
I raised my hand because I'm participating as a participant, not a moderator. But so there, I'm not sure because like there are words such as da and ah, and basically they occur with everything, and their vector embedding is basically just meaningless for that reason. But then it's hard to say if they actually associate with anything, so that manipulating it would affect. I'm not sure if that addressed.
I think what I'm trying to say is that there can be, it's kind of like I know because you're doing the NLP thing, so it's kind of like those tokens that, like stop words that you drop, but you can actually have embeddings that have no word. You could have a vector position that has no word associated with it, right? But you'll have like a cluster of other embeddings around them, so it's like there's different ways of actually describing the underlying structure of the representation that has no actual literal token associated with it. But they act
Kind of like a k-means sort of thing, where you'd like
sounds
look
like
at clustering.
K-means and principal vectors, these eigenvectors, these are all different ones that we have names for, but they don't always have. Or sometimes they're very convoluted things that are emerging as a consequence of the metric that you're using and stuff like that.
Okay.
I'm just pointing to the fact that there are these other mathematical properties about what we're doing that we
Right, that could be interesting to explore.
idiosyncratic.
Yeah.
Cool.
Cool.
remember the details of the very first paper that was cited, debiasing word representations, but I think they kind of do something similar. I don't know if you remember the name.
The paper that's man is to computer programmer as woman is homemaker. Yeah. So they do.
Could you repeat the comment, please?
Okay, so she was saying that paper that I just named does, to some extent, find these principal components inside your word embedding, and then use that as your sort of gender axis or whatever bias directional axis. And yeah, that's exactly it. So they'll look at definitional sets of words, like he, she, man, woman. So a list of kind of like words that are supposed to differ only in gender, and then you take the difference of those words, and so there's sort of, you can imagine a vector connecting each of those different pairs, and then what they do is they run PCA on those directions, and what they find is that the vast majority of the variance is explained by the first dimension. So basically saying that all those vectors point roughly along the gender axis, and then they use that as the gender axis in the space, and they project words back down onto it. So yeah, exactly. So it's finding these type of geometric structures inside the embedding. Yeah, exactly.
So the title of I'm just saying this for the camera. The title of the paper was
Man is to computer programmer as woman is to homemaker.
That was the title.
That's the title of the paper. Yeah, exactly. Oh, maybe it does. Maybe it does. Yeah.
It may start with debiasing word vectors.
I can show I think I have a references slide here. So it's this first paper here.
It ends with debiasing.
It ends with.
Oh yeah, okay, it ends. Yeah. There we go.
Any other comments, questions? All right, beautiful. Let's thank you.
Thanks, guys.